Hello, everyone. In this presentation, I will go over our work, a minimal subset approach for informed keyframe sampling in large-scale SLAM. SLAM faces significant challenges in large-scale missions. Typical LiDAR SLAM systems use a front end for odometry estimation and a back end for refining the trajectory through loop closures. However, loop closure detection in large environments is computationally demanding, as it requires identifying and verifying thousands of candidate pairs for pose graph optimization. Keyframe sampling is a common approach to reduce graph complexity, but conventional methods relying on spatial heuristics often lack adaptability to diverse environments. This can result in either retaining redundant information or discarding critical data, ultimately compromising performance. Based on the aforementioned, the main contributions of this article can be summarized as follows. To the best of our knowledge, this is the first paper to propose the joint keyframe sampling problem, which we establish as a unified formulation that connects place recognition, loop closure detection, and their downstream impact on pose graph optimization. By framing these components as a coupled problem, we highlight their mutual dependencies and reveal key theoretical and practical challenges that have been largely overlooked in existing literature. We propose the minimal subset approach, a keyframe sampling strategy that balances information preservation and redundancy minimization through a sliding window combinatorial optimization. By introducing principled metrics to quantify descriptor space, redundancy, and information content, MSA selects a minimal set of keyframes that maintains loop closure potential and pose graph consistency while remaining suitable for real-time application. Through our results, we demonstrate that MSA enhances scalability and efficiency by reducing computational demands. It consistently achieves lower false positive rates in place recognition and superior absolute trajectory error, ATE, and relative pose error, RPE, in metric localization across diverse environments without manual parameter tuning. By minimizing loop closure query time, memory usage, and the overall time required for pose graph optimization, MSA is well suited for large-scale missions. The first part of our approach is redundancy minimization. This metric captures the redundancy between keyframes by comparing the similarity across consecutive descriptors. Next, the information preservation term analyzes consecutive keyframes to calculate the gradient of features based on pose changes. We extract the principal components and transform the descriptors accordingly. This step allows us to quantify the information preservation within the selected keyframe set. The final step is the sliding window optimization, with an example shown in the video on the right. For an adaptive sliding window of n keyframes, indicated by the frames above the car, we compute the optimization terms for all possible keyframe combinations. Then the keyframes that minimize the joint optimization function are sampled, visualized with a green marker above them. As new samples enter the sliding window, the descriptors are visualized on the top left of the footage. In the middle, we demonstrate the Jacobian, which shows the gradient of features across pose changes, while on the right, you can see the transformed descriptors. Overall, we observe that the next sampled pose adapts to the environment and the car's speed. Notably, when the car slows down, 2 samples are skipped, and when it speeds up, only 1 sample is skipped. We perform large-scale evaluations in the following datasets. The Apollo South Bay Sunnyvale Big Loop sequence that spans over 100 kilometers, and the 30-minute Newer College Park sequence. The experimental results show that the overall absolute trajectory error, the relative pose error after incremental pose graph optimization, as well as the false positive ratio of place recognition, are lower than those of other adaptive methods, such as entropy-based approaches. Additionally, we demonstrate that keyframe sampling can significantly reduce memory overhead by minimizing the number of keyframes. This leads to improved processing times for both incremental pose graph optimization and loop closure detection on a per-frame basis. Thank you for watching. For further details, please refer to our article.